All right, thank you very much. My name is Manuel Egele. I'll be talking about some fuzzing work that we've done over the last year. And while I'm up here, so I'm the one in italicized font up there, really the bold font is on my student. All the work that I'm presenting has been done by Alexander Bulikov, who really should be giving this talk, but he's on his internship at EPFL, so across the ocean, kind of far for this evening. All right, we'll change things up and talk about security. You might wonder, what do I care about security? Anyone using gas in their car? No one? Great, everyone's driving electric. For those of you who have gas, anyone remember Colonial Pipeline? Well, that one got hacked and then caused a bit of a ripple in gas delivery across the eastern border of the United States. Anyone running Qemu in the cloud? Anyone running any private cloud will most likely be running Qemu or VMware for whatever reason. When you're running cloud, you're probably concerned about hypervisor escapes, such as Bandan. Anyone using Linux? Great, now I get a lot of hands. When you're running Linux, you're often concerned about security vulnerabilities that give you privilege escalation, such as dirty cow. And so today I'll talk about the last two things, your gas problem, buy an electric car, and then you're done with that. All right, so from a security standpoint, what we really want to do to make these things less annoying, these things being security vulnerabilities and bugs, is to find those bugs and fix them before the bad guys do. That's good posture. It's also good for finances, because Microsoft says that for any public bug that they have to report, they're spending on the order of $1 million. So whenever they have to do a security advisory, it costs them a ton of money. Better not have those. Nowadays, the most prolific way to find those bugs is by using a technique called fuzzing. So what is this fuzzing business? At the end of the day, they take a system under test, be it your hypervisor, your Linux kernel, your programs, you name it, and give those systems under test random inputs, and then you observe how those systems behave. And so I've bold-faced here inputs, because what this talk is about how we actually make inputs that are useful to fuzz hypervisors and operating systems kernels. Once you have this capability, you repeat. You repeat thousands of times per second, and you repeat this for a CPU decades. And you don't do it on your own infrastructure. You have someone else pay for it. We'll get to that at the end. So some examples is why fuzzing is successful. It turns out that Microsoft engineers were complaining about how good their Sage fuzzer was. It reported way too many bugs for them ever to be able to fix it. So that was a good start. And Google's open source fuzzing framework right now supports over 850 open source projects. They found over 28,000 bugs, over 9,000 vulnerabilities in the last 6 or 7 years alone. So really successful in teasing out those bugs and vulnerabilities. As I promised, I'll talk about inputs, because it turns out that giving inputs to your programs, for some programs, those inputs are simple. So we might see programs that consume image files, PNGs, JPEGs. Those inputs are fairly straightforward, so you can almost literally go with random. However, if you have other programs, such as a PDF reader, where all of a sudden you have a lot of structure to your input files, or you have hypervisors, or you have operating system kernels and your system call boundary, your arguments or inputs become now very challenging to deal with, and this arises essentially from the semantics that is imposed on the data for those inputs. So how do we deal with challenging inputs? Historically, what has been done is that someone sits down, manually writes a grammar, and then we draw inputs at random from that grammar rather than truly random inputs. That's great. It's a lot of manual work to develop those grammars and also hide some of the bugs. What we did instead is we reshaped the input space so that we can take truly random information and just provide it in the correct form. And we can do this by essentially observing how inputs are being consumed by the systems under test, and then have transformers that morph random inputs such that can be consumed by the systems under test correctly. So how are those inputs consumed? We'll have two quick examples. One is on system calls for the Linux kernel, and one is for the hypervisors. So the Linux kernel, fortunately, cannot reach out to userspace directly. It will consume information from userspace either via registers during a system call, or use get user or copy from user to access userspace information. So by realizing that, we can simply put random information at the correct places and then use traditional fuzzers to tease out new bugs and vulnerabilities in the Linux kernel. So this is fresh off the presses. Alex gave a presentation on this paper earlier this month in San Diego. Here's a little overview of how it works. Don't worry, I won't stab through it. Really, the takeaway is, historically, we have these grammars, so 33 pages that cover only the KVM subsystem in the Linux kernel. What we get with our system is essentially 7 lines of configuration, finding more bugs and bugs in code that has already been covered by previous fuzzers. I'll skip the detailed results here. So in total, we found 9 new bugs, including 5 bugs in code that already has been fuzzed by the industry standard syscaller fuzzer. Now switching gears, talking about how we can fuzz hypervisors with exactly the same technique, right? We realize the salient points of how the system under test consumes inputs, and then we morph truly random inputs to the corresponding input channels for the systems under test. So what we did for virtual devices was exactly the same thing. We realized those input channels, there are 3 for virtual devices, just on a physical machine as well, at least on an x86 machine. You have port I/O, memory mapped I/O, and direct memory access. If you look at how complicated it is to deal with those things, port I/O is pretty simple, memory mapped I/O is a little bit harder, but still pretty simple. And then when you're trying to deal with DMA, all hell breaks loose. Nonetheless, we also put that into production. We wrote a paper on it that was published last year at Linux Security. And again, all the work was done by Alex. Here we have a little overview of how the system works. Again, not going into the detail. If you're intrigued, please read our paper, hit me up in the break, and I'm more than happy to talk about it. The core idea that we have here for this paper was essentially to take all these dispersed memory areas and funnel them together into one consistent memory area that can be easily fuzzed by a fuzzer. So how was that evaluated, and what are the results from that? We fuzzed 33 virtual devices, many of which are enabled by default when you're running Qemu, so most of your clouds will run this. We found 66 new bugs, and we found whatever is left to the 110 from bugs that were discovered by previous work already. Buffer overflows, use after free, the whole garden variety of your security class is part of this paper. We found them all. We found all the flavors, not all the bugs. Just want to make sure I'm not saying something wrong here. So yeah, these are the research outcomes. I wanted to spend the last few minutes of my presentation to talk about outcomes from our research that are not purely on a basic research angle. So in the previous talk, we heard that there are efforts ongoing to upstream research prototypes into open source projects, and that's exactly what Alex did as well, because he's not content with just writing papers, he's also making his software useful for everyone on the planet to use it. And so our Morphos fuzzer is a part of Qemu in the main branch, so if you download Qemu today, you'll have Alex's code on your system. Furthermore, Alex managed to get Qemu, the open source project, accepted at Google's OSS Fuzz infrastructure. This is very nice because now Google provides the resources to continuously run our project on thousands of CPUs, day in, day out, 24/7, right? So all the code is on GitHub, of course. Here we have the screenshot that shows that Qemu was actually part of OSS Fuzz, and the last commit, as you can see, is also done by Alex. I took this screenshot yesterday, so it's fairly up to date. So Morphos is an open source fuzz. That's great for security purposes. Now, if you are a developer contributing code to Qemu, you might not like Morphos as much as the security people do. Because let's say you're writing a new backend for Qemu, like the Intel Gigabit Ethernet networking support for the E1000E device. You get your code admitted into the Qemu repository, you're all happy, and the next thing you know, you get an email from the automated system at OSS Fuzz that says, oops, you made a bug. So that's what our infrastructure is currently doing. It'll check whatever the commits are, they go into Qemu to find bugs, hopefully before the bad guys find them, and can exploit them. So in summary, Instead of sitting down and manually writing grammars, what we do is we reshape input spaces so that we can give random inputs to systems under test that consume complex inputs. And the goal is to find bugs and vulnerabilities before the bad guys do, and therefore make systems more secure. At the end of the day, we have the papers to back it up, we have the systems to back it up, we made your clouds more secure, so you're welcome.